I'm Nick Booth. I'm a principal data scientist here, and I'm going to talk to you today about some of the things I've been doing exploring end-to-end audio redaction. And please feel free to interrupt, ask questions. I think I prefer a more casual approach. So, generally, what I'm going to start with is just describe what the problem is, what actually am I trying to do here, what data set can I use for this kind of problem, a few approaches that I tried, and then where this could go in the future.
Can everybody hear in the back?
You good? So, if you were going to go do redaction, you've got some piece of audio and you want to remove something. You've got some sensitive audio, maybe a phone number, an email address, something. You need to do, there's usually a few steps in the conventional approach. You have to first, you've got raw audio. You've got to find some way of removing some segments of that raw audio. And traditionally what you would do is you have some kind of speech recognition system. So you're turning the audio into text. And that can happen a few different ways. This is more or less a Colby. Let me first ask, how many people here are familiar or comfortable with speech analysis, natural language? Has worked on that to some degree in the past?
NLP, yes, speech.
Okay, then I'll go really starting from the basics. So for an ASR, like Google transcription, what you would do, something like this, is basically you take the raw audio and you extract features. You want to figure out what is going on in that audio. So those features can be things like I-vectors that correspond to individuals. So an I-vector would have kind of speakers embedding. As well as MFCCs, mel frequency sequestral coefficients. They're basically tuning the spectrogram to human ear reception. So those form the input features to a neural network. That neural network's trained just to take that input set of features and output phones, what sounds we think went on in that audio. And then you have a sequence of phones, but we need to know what that actually constructs because the phones don't necessarily tell us what the transcript is. And the phones might not match perfectly. People say things different ways. There are non-native speakers that won't be able to construct the same phonemes. You know, there are languages where you don't have the TH sound, and so you have to say F, and we need to be able to handle that. And that is handled with something like a language book. Colby uses hidden markup to construct the likely probabilities as you pass through this graph. And then the one that has the highest probability is your most likely transcript. So then you end up with a transcript that is, NVIDIA's cool, right? That's great, but let's say that I want to redact any mention of companies that make GPUs. So we got to remove NVIDIA. Then we construct the second model. And that models that this is now text-based. We don't have to worry about speech anymore, now we have text. So we construct an NLU type of model to recognize NVIDIA, AMD, Intel, etc. And we find that, redact it, we could use Redaction, we could use all kinds of things to find that recursive speech tagging to figure out where that GPU company is in that text. Once you've done that, you then need to figure out when did that happen in my audio, because we don't know necessarily, we just have a transcript. Using the timestamps, we can then redact the audio, and then we've got a nice clean bit of audio. Now, as I've described that, that's a lot of steps, right? There's a lot of a pipeline of processes that we have to go through in order to actually redact what we want to redact. So what happens if we have failure anywhere along that pipeline? We won't redact what we want to redact. Let's say NVIDIA is not in my language model. I don't know that word, right? I end up with video, and now it's not redacted. But the audio still says NVIDIA, it's just my language model didn't recognize it. Or let's say that the features aren't very clear, and there's a failure, and we don't understand NVIDIA, we just get a the sound, and it constructs just the same. And now we're storing sensitive information. So that's the problem, is this pipeline approach. And I really call this a propagation of errors. Any error along the way can expand and grow. I was thinking about polarizing lens, my background in physics. You can, you've got some likelihood and it decreases as you kind of keep multiplying with 0.99 times 0.99, etc. You'll have more and more problems. So that's one issue. The other issue is that you might be sensitive, or let's say that you didn't build your own ASR model. You didn't build this yourself. You're using Google's. What happens if Google doesn't have a video? How do you redact now? Right? You now need to say, okay, well, video is close enough. Then I'll look for video and redact it, but only in these certain cases, where it matches the parts of speech. Now you're really sensitive to somebody else's model that you don't have any control over, and that can be dangerous too. So, what I'm going to talk today about is an end-to-end solution, where we don't have the risk of propagation of error because it's just one model. So, audio can be directly redacted, and then we don't have to worry about storing sensitive information. So here's an example of the original audio form, and then you can see the censored out segment. I don't know if it's going to work for me. Is that going to work out of the box in the way?
Yeah. I use it.
Oh, yeah? Okay. So, the project that I'm going to work on is...
Has a base picture.
Nice. Okay. The project that I'm going to work on today is redacting numbers from speech. It's not really a complicated or realistic problem, but it's a toy model that we can play with and see, is this approach appropriate and will it work? But first we need to get a data set. And what I need to do is figure out where are numbers in this data set. So I'm working with LibreSpeech. It's a data set of many audiobooks, about 1,000 hours of recorded speech, freely available, 16 kilohertz data, sample rate, all English, and generally pretty clean with high quality transcriptions that I can trust. So using those transcriptions, I can identify where the numbers, or what the numbers are, what are numbers, and then figure out where they were and generate a target sequence to extract what needs to be redacted, what's okay to keep. So first, how do we figure out what's a number? I use Duckling. I don't know if anybody's familiar with Duckling. It's a rules-based program created by Facebook, I believe, written largely in Haskell, and it basically uses regex. It's not very dynamic, but it doesn't really need to be. Somebody spent a lot of time developing an insane number of rules on how to extract various dates and credit card numbers and functions. The issue, though, is that it doesn't exclusively extract numbers. It grabs a lot of additional information. So, 3 cups of sugar, it can extract all that and figure out the quantities and the units and all that, which is great. But I really just want the 3. I don't want the cups of sugar. So we have to do a little processing to clean that up. Ultimately, that's going to be some work. So I processed the LibreSpeech dataset, created a list of tagged words, which includes cup of sugar, and then figured out how often they were tagged versus untagged, and then created a set of just numbers. And I'm going to call these my elementary numbers. These are 57 words that will form any number in my data set. Okay. From this, I can construct any number that exists in that data set. You'll notice there's no trillion here because they don't say trillion anywhere in the 1,000 hours of dialogue. But if I said 187, you can find 187 in that list. So now I know what a number is, which is great. You would think that'd be easy, but not as easy in text. And I'm going to create an output sequence. We want to be able to figure out what we need to redact. So using the transcript and the set of elementary numbers, this is very simple. Just read through the transcript and figure out, okay, redact, don't redact, don't redact, etc. So if I said I bought 7 apples at the store, my output sequence should be n, redact, n, right? Corresponding to each of the words. We met 3 days later, you can see the same pattern. So after selecting just audios from the Weaver speech dataset, yeah.
If there's something where there's like 74, is that 2 stars or 1?
So 74 would be, you'll see 70, and then there should be 4. So there would be 2 stars in this case. So I'm treating them as individual words. So then audios that contain these elementary numbers, we end up with only about 30,000 recordings, which is relatively small. So now I need to create a model. And my model needs to learn 2 things. I'm trying to train it to output these sequences. It needs to learn 2 things. The word segmentation of an audio input, where the word boundaries are. And then it needs to learn the actual thing that I care about, the tagging of the word level tokens. This is sensitive and this isn't. Now, there's some issues. This can't be implemented as an end-to-end solution because I won't know when those words were said. I need to then figure out when those words were said to then redact it. So that requires some post-processing. But it's a proof of concept that we can play with to say, okay, it is learning these words need to be redacted, so we're along the right path, at least. I used an encoder-decoder type of model. I'm not going to go into too much detail, but if you want to see the model, it's actually used in this paper here. I realized that a completely different application could use the same model in this case. So I directly applied it. If you want to read more, that's the paper to go for. But basically, their model took an audio input and was trying to encode the intent. So turn the kitchen lights on, okay, for kitchen lights on should be the intent of that message. Right. So for the word level results, I trained the model, converged all right, but ultimately fairly poor results, which happens. But remember there were the 2 objectives, discovering where the word boundaries are and redacting those particular words. And when I look at the prediction and the truth, I actually see that the redacted sections look like they're showing up in kind of the right spot. They're showing up like this P, this redacted bit, is showing up just past halfway in that audio. And likewise, I have 3 redacted segments in this next section, but the spacing's wrong, right? And same here. So what that seems to suggest is that I'm just doing really poorly on this first objective. Discovering where the word boundaries is challenging, which is not surprising because when I speak, it's not like you can clearly see that. If you've ever listened to somebody speak in a foreign language, you can tell, it's hard to tell which word, like what's an individual word because it just seems like it all flows together. If we're not familiar with language, then we won't be able to find the boundaries. So instead of this semi-subjective approach, what if we take a more objective approach? What if we make our segmentation based off of time, right? What if we cut it by every 0.1 seconds and say this is sensitive, this is not sensitive. So let's rewrite it and create a new output segmentation based on the time level. And so I bought 7 apples at the store might show up more like this, depending on how long it took me to finish these words. Again, this presents a new problem. I need to know where the words were in the audio. So this is a new problem to solve, and it's you can do it a few different ways. One way is to use force alignment. I know what my transcript was, I know what the audio is. So you can do something like this. This is a Montreal forced aligner. If I have a transcript, I can decompose these words into the phones, the sounds that make up those words, or are likely to depending on the dialect, depending on the regional variation, etc. And then I can use a language model, an acoustic model, to try to match those phones into the audio in each of those places. And I'll do my best to match that individually with individual phones, and then triphones, the surrounding two phones on either side, and then with some adaptation to that particular speaker. And then we end up with timestamps for each of the sounds. From there, we can reconstruct back to the full words, and then we have timestamps for the words themselves. For the start and stop timestamp for each of the words. And then creating the target sequence is relatively trivial. I have the start and stop times, I can then create the target sequence. So now we have two new targets to learn on this new model. We need to learn the total length of the audio file, which hopefully is easier because it is objectively dependent on the input audio. And then I need to learn what time segments need to be redacted. And this question might not make any sense to those who haven't worked in voice before, but why not 25 milliseconds? So the reason I mention this is because 25 milliseconds is very commonly used as a framing for audio processing. But ultimately, we end up with extremely long target sequences that become very difficult to train. Anywhere between 9 length to 600 length output sequences. And training that can be overwhelming, especially for the size of the data set that we're looking at. Here we have the results of the new model. Again, you see the alignment is an issue. It's a consistent issue. But rather than discard or just try to apply this, I realized that as long as the shape is roughly correct, we can apply a scale factor. There's no reason to be very strict about you need to get the length right if the shape is appropriate. So I applied a scale factor and multiplied the timestamps of the individual start and stop of the private numbers in order to stretch them to the appropriate length or shrink them, depending on the problem. And what we see is the recall and the precision, the amount these boxes overlap improves greatly, right? Which is, it's still not great. It's 70, 0.7 is fairly good, but it's not amazing. Okay.
So are you still using the 57 number code for all the fees in this case? So how are you finding the non-fees? Are you using another data set for it, or everything is not P falls into?
Everything that's not P falls into the end. Yeah. Because I know that my numbers are exclusively these sets, this 57 numbers. And so as long as it's not one of those, it should be that. Yeah.
Do you know what could cause it to shift like that?
I suspect that I'm going to go back to the model. There's inevitably some compression when you are encoding the data, and we may be losing the overall length to some degree. I think that I'm going to talk about this in a minute, but I think there's some value to constraining the length of the output segments because we know ahead of time the input length of the audios. So there's no reason that I have to guess how long the output is. I know that it took 5 seconds to say it, so there should be 50 targets, 50 length target sequence, right? Yeah. So in any case, I find this encouraging. But there's the question of, I wanted to do some error analysis at least, figure out why we're not doing great on some of these cases. And one of my questions was, is there dependence on the word being redacted? Right? Is a specific word more or less successful? Because the reality is we have 57 targets of different words that don't necessarily have anything to do with each other. Because I haven't accounted for the language of English. We just know it's a sequence of sounds, really. And so what we see is the performance, especially of 1, 2, 4, and 8, is not amazing considering how often they show up in the data set. And I would note that all of those have pretty common homophones in the English language. And that could be an issue, because sometimes those sounds, the sequence of sounds, is tagged as a number and sometimes it's not. There are also maybe issues with limited training data. We have, only 300 examples of the word million in the entire data set, which is rather limited. I also wonder about cannibalization, which I would say like third and 30, and notably on the opposite side of this accuracy of we call it precision scale here. Third is very nearly a subset of 30, so that could be a factor as well. The other thing that makes me think that the other thing that I found that was interesting was Fortnite. I noticed a few examples like this became censored, became nice. And that tells me something. It seems to suggest that we're not recognizing words so much as we're recognizing directly sequences of sounds, right? Of phones. And that means a few things, that homophones can be challenging. Anything that sounds identical is going to be confusing. But it might actually be an advantage in some cases. In the case of censoring swear words, people can be very creative with their swearing. And so if I said absolutely, I can still recognize that. An ASR might fail because it might not have that curse word in its dictionary, but I can find that sequence of sounds in the middle and redact it appropriately. So depending on your application, this actually may be useful. But it does depend on what your goal is. So there's some interesting future work. I think that the next step that I'd like to do is trying to figure out how to solve the homophone issue. Ultimately, I think we need more of a language understanding and grammatical understanding in order to distinguish, disambiguate between 2 and 2, C, C, and C. These things are identical when I say them, at least in this dialect. So I'm still investigating how you might encode that distinction. The other issue is probably that there are shortages in data, which could contribute a lot to performance. And like I said, I think I'd like to constrain the output sequence length. But yeah, it looks like I was encouraged because I was able to actually identify some of these words, and it was really kind of a shot in the dark to see how successful this kind of thing would be. So now I'm going to open up to questions. Any further questions?
I have 2 questions. Like precision and recall of standard ASR these days, and then for the ASR at this point, how long does it take from speech to having whether something is determined or not? Could this be used for real-time communication, or is it only a usually do there?
So for your first question, ASR performance. You're talking generally ASR performance?
In general, anything for your use case, if you're comparing yours to an actual ASR.
That's a good question. It's probably something I should have just checked. The issue.
So one way to measure ASR performance is to look at this metric called word error rate, right? Which is basically how many words are substituted, deleted, or added compared to the ground truth. And if you take a look at the recent literature, some of them would claim that you have word error rates of close to 0.05 or 5%, which is approaching human level word recognition. The problem is that channel condition, which we cannot control. So most of these tests are run under optimal channel conditions where there is no external noise and there's nobody talking in the background. So under those conditions, you might get reasonably good word error rates. But under other channel conditions, you might get slightly worse word error rates. Now, some of the other things that we have done here at Vail is that we have tried to take a look at certain domains that have a restricted vocabulary, and instead of using a general purpose ASR, try to train an ASR engine with that restricted vocabulary only. And in those cases, what we've observed is that the general ASR gives you a word error rate of almost 0.33 or 33%, and our bespoke ASR gives you a word error rate of about 0.11 or 11%. So that's, that runs the gamut basically.
Now, the reality is most research is conducted on quite clean data, and the real world truth is that a lot of data exists as telephony or, just strictly speaking, noisy data.
I guess that's actually a third question. If you choose any noisy data, like add some noise to all of your sounds to see if it improves the result.
For this project, no, I haven't played with noise or augmentation much, but no, I think that would be a valid approach, a valid way of getting a little more value out of the data. Yeah, did I cover all your questions?
How long does it take to actually run it? Just use the real-time communication and post-processing.
So you'll notice that the output to this model is a sequence of timings, right? So it would still need to be a secondary step to redact, but the amount of time that this takes to infer is negligible. It's a quick process to infer to get the sequence output.
So you have a few second delay.
Yeah, possibly less depending on how you build out this kind of system. Yeah.
How did you, for the kind of the numbers that the word numbers that you had, how did you account for things like O or zero?
Yeah, in this case, it wouldn't be well accounted for. The data set in this particular case is unlikely to have O or I'll say non-conventional ways of saying numbers, just because of the context of the data set. The domain is an audio book, so I feel like they're probably not likely to, speak in more of a slang. But I think it would be partially captured by duckling. You'd have to be careful that you're not tossing it out with my cleaning method, that you're not untagging it because it shows up a lot. That's just the word O or the exclamation O. But duckling's rules cover a crazy amount of use cases, so I wouldn't be surprised if they take O as a number in certain contexts.
So can take care of the some people say 150.
Yeah, it should. Yeah. It's text-based programming. I think they still have a demo that's running somewhere, so if you want to play around with it, it's interesting. But it definitely has its problems as well.
OpenAI recently released their open source Whisper. I think transcription and I think also translation. Bilingual translation library. Take a look at that.
DJ has more to say about that.
Yeah, we have taken a look at that, and I think as a general purpose ASR engine, for instance, or translation, it's actually pretty good. But when you use it under certain conditions, like we were using it for our purposes, where our recordings are coming over G711 codecs, for instance, I found out that for short utterances, its word error rate for Whisper turned out to be 38%. So I think it's a good tool, but I don't think it's a good tool for every application.
What were their published metrics for English language?
The published metrics for English was close to, I believe, something along either 7 to 12% word error rate on their purposes.
So yeah, I think it again shows that the training sets that exist out there are not comparable to the real world in a lot of cases.
And what was interesting to me is because it's a multi-purpose model, it actually recognizes something like 40 or so languages. But some of the languages that it recognizes have word error rate that exceed 100%.
Okay.
So clearly, In most industrial applications, if the word error rate exceeds something like 20 to 25%, then for downstream purposes, it becomes all but useless.
Didn't you say that also you were seeing generative?
Yeah. And the other interesting thing I saw is I took a recording. So the recording is the same. I didn't change the recording. And I gave it to Whisper. And every time I would give it to Whisper, it would give me something completely different. And not only would it be different by the contents of what it transcribed, but the length of what it transcribed would be different as well. And the only thing I could think of, and I haven't studied this in more detail, is because it's a generative model, sometimes it abstracts and puts words that probably, it thinks are right, but are not quite. So I think Whisper is a great tool. I think I'm glad that OpenAI has open sourced it. But I think if you use it in production, you have to be careful.
Anything else?
So you explored time-based and sequence-based approaches to essentially segmenting your segmenting speech. In financial markets, there are other ways of segmenting the trading activity. Sort of like volume-based approaches, for example. So there you might look at, for example, the size of the waveform and the volume of the speech being used to maybe at the start of look for large strong deltas in that volume, say, to recognize this into a boundary. So that you can then say, okay, here's the volumes. I don't know how you do this. As you mentioned, the speech running together.
Yeah.
Have you looked at that?
I haven't played with it. It's an interesting thought of trying to do the segmentation for it, the model essentially, right? You can, or look at other aspects to help do the segmentation. I don't know. I think a lot of those variables would be encoded in the inputs, and so in theory the model could learn it, and obviously hadn't. But it's something that I need to explore more to say definitively that it's not taking advantage of for example, like natural gaps or volume changes.
Yeah, so it's kind of related. So like, have you tried using any of the data set to remove the noise so that combine it with the one that you have, so that the distribution is more accurate? Because we have one that has like 10 edges, one has 8. If you're able to spot the 8 more accurately, would that decrease the chances of going wrong? I mean, you're adding way more data, of course, which makes it worse in a way, but
Yeah, I mean, to me, are you getting at telling apart the homophones through additional data, or not? That is the question.
so more like removing the non-57,
The non-what?
the non-57 that you're trying to train, but trying to remove the other words in order to train it better. So like you have another data set combination, like a normal basic, English one, to remove the other ones to better identify where the 57s are located and train it that way.
Yeah, I haven't played with additional data too much. This was ultimately, I need to spend more time playing with this to fully, develop out the project. But I think some of the problems we definitely be solved with additional data to better fill out the diversity of numbers that exist. So yeah,
I think we have time for one more question.
if there's one.
Thank you very much.
Do you want to?
Yeah, we want to